Right, if we could have the first talk.
Okay. My name is Sriharsha, and I work as a machine learning engineer at Woodsano. So this was a project I worked on last year, a joint project by St. George University Hospital and Kingston University. So the project was to develop an artificial intelligence diagnostic tool for pediatric distal radial fractures, a proof of concept study. So we would like to acknowledge AO UK. This project was funded by a research grant from AO UK. So the problem statement or epidemiology is, in the UK, 1 in 50 children will sustain a fractured bone yearly, and 34% of children sustaining an injury do not have a visible fracture on initial radiographs. So 25% of all children fractures involve the wrist, and the incidence is increasing. So it's quite an economic burden because annually 2 billion is spent on this, and in UK, pediatric orthopedic relation litigation cases cost over 3.5 million pounds, whereas average payout of between 28,000 pounds and 57,000 pounds per case. So it involves time of work for parents because they have to look after the children, and attendance at outpatient department. So children also miss schooling. So if you look at the current trends in pediatric distal radial AI studies, we found out that there is ultrasound images and combination of AI for that to predict and diagnose a condition, or a distal radial fracture AI tool that can predict if there is a fracture or not for adults, and pediatric fractures in the entire skeleton. And so the limitations are, we have very limited data set in terms of developing an algorithm to predict. So the aim of the project is to develop an artificial intelligence tool that can recognize if there is a fracture in a given radiograph or not. So we wanted to label the radiographs first, given radiographs into fracture and no fracture, and then train a model, and then validate the model using how many times it predicts fracture to be fracture or no fracture to be no fracture. So the methods we employed were patient involvement questionnaire was taken, and then it is a collaborative effort from three teams: radiology team, orthopedics team, and computer science team. I represent the computer science team today. So a convolutional neural network was trained to recognize what a fracture is and what's not a fracture inside a given image. So a HRA ethics statement has been approved, and then tripod statement checklist has been applied because it's a diagnostic and prognosis for, so it's a prediction model that uses that's used for prognosis and diagnosis. So 5,000 retrospectively collected pediatric wrist radiographs from 2014 to 2018, and poor quality images were excluded where there's a lot of noise in the image and you can't really get any information from that image. So these kind of radiographs were excluded before training a model. So anterior, posterior, and lateral images were included because in the previous studies we've noticed that only one of these forms were included, say anterior, posterior, or lateral. We wanted to include both of these. So we've also included radiology text reports. So the first step of developing a machine learning model is to try and process the data. So after collecting the data, you de-identify the data and then use DICOM software to visualize the data and understand the metadata inside the radiograph. So you have patient information, patient name, date of birth. So this information is anonymized before you try and train a model. And this metadata is converted and stored in an XLSX file to make sure when you try and label the images, you know what fracture corresponds to, what radiograph corresponds to what fracture and no fracture. So in that way, we've separated them, and a DICOM data converted to high resolution PNG image. So these DICOM images were converted to PNG images because a neural network doesn't take in DICOM format images.
So you've got 1 minute.
So we collected 239 images, and then image augmentations were applied to make sure data is increased, and a Python script is used. So horizontal, vertical, and zoom augmentations were applied. So if this is the original image, then it's flipped to this to make sure data set is multiplied. And then we gathered about 5,000 images, and the training set was 70%, and validation was 10, and test data is 20%. So after training for 20 epochs, the diagnostic test accuracy was 85%. So this is what the graph looks like for training. The training accuracy peaked at 96%, whereas the validation accuracy means somewhere about 86 and 85%. So that's what the orange line represents. So further diverse data needed to test the robustness for all noise types. So if you see the red arrow, it's the noise type that we want to de-identify in developing a future model. So we also wanted to develop explainable AI.
I think you just want to wrap up.
So we want to develop an algorithm which can draw a bounding box around the fracture itself. So, yeah, that's all.
Thank you.
Thanks.
Right. Have we got any questions for Sriharsh? Yeah.
Can your model be used to train the AI to be better than a person looking at X-rays, given that the input that your model is based on is all from a clinician looking at the X-rays and saying there is a fracture?
So just for the recording, the question was, can the model be trained to be better than a human because it's based on human interpretation? Is that right?
Well, ultimately, labels come down to people labeling the image itself. But then if you look at other techniques like reinforcement learning, you can have a model trained based on recognizing what a fracture is, ultimately, using the existing fracture images, and classify them using unsupervised learning. Instead of having to label them manually and do it, you can use unsupervised learning techniques and form a cluster of images saying fracture or no fracture, and then manually diagnose that and improve the model. Yeah.
Naomi?
Thank you. I'm not sure this is a question for you, and I don't begin to understand the AI, so thank you very much for explaining it in a way that I kind of nearly do. I guess it's a question for somebody else, which is really the why. I don't think I recognise the sort of sickness load that an undiagnosed minor distal radial fracture brings, and maybe somebody here can explain that. I might be missing a point somewhere, and I might be missing a whole load of stuff.
I can explain that. So about 30% of the outpatient appointments in ED, when you X-ray, there's actually no fracture, and then a lot of those would say come back to a fracture clinic. And with this AI model, what you could potentially do is change the patient pathway. So rather than then coming to ED, you could have them come to say a hub in the community, have the X-ray. You peel off that 30%. You don't need any further treatment with advice, and then you're just seeing the patients who actually need a plaster in the hospital. So it's reducing the disease burden, the pathway, and then the time off work for parents and schooling missed for the kids having to keep coming back to appointments they don't really need to come back to.
Right, so you're trying to not diagnose, you're trying to confirm the lack of a fracture or lack of a serious fracture rather than find a fracture that might be more serious.
Yeah, so with this initial model, what we're trying to do is say, is it a fracture or no fracture? And then what you would want to do is then refine the model, and you could potentially diagnose what type of fracture it is, or pick up incidental findings like tumours, but that's more technical training of the model and the larger data set that you need. So to just start with, you need a proof of concept to say you can diagnose whether there's a fracture or no fracture.
Can I ask one question? In terms of age, did the model change based on the age, the accuracy of the model?
Yes, it did. So currently, these radiographs were collected from to an age of 19, and the model peaked at 86%. But if you looked at the literature review where they were collected after the age of 19, say adults basically, the model performed 96%. I think it has more to do with the premature age of the bone itself.
Yeah, I just wondered how it coped with the growth plate of the physis.
I see. I'm not really.
No, that's cool. Okay.
Thank you.
Brilliant. Thank you very much.